Question 1. The performance metrics show a significant increase in the time taken from patient arrival for PET/CT scans to the completion of image acquisition, alongside a slight increase in the number of repeat scans due to suboptimal image quality. Which approach best addresses these performance issues within the framework of IEA professional certification standards for diagnostic imaging? Option A. Immediately increase the number of PET/CT scanners available and extend operating hours to reduce patient waiting times, assuming increased capacity will resolve the throughput issue. Option B. Implement a new image reconstruction software package that promises faster processing times, without conducting a full validation study or retraining the imaging staff on its use. Option C. Focus on reducing the time technologists spend with each patient by streamlining patient positioning and scan setup procedures, without altering the imaging protocols themselves. Option D. Conduct a comprehensive review of the entire PET/CT imaging workflow, from patient scheduling and preparation to radiopharmaceutical administration, scan acquisition protocols, and image reconstruction, involving technologists, physicists, and radiologists to identify bottlenecks and areas for protocol optimization and quality control enhancement. Correct answer is D. Conduct a comprehensive review of the entire PET/CT imaging workflow, from patient scheduling and preparation to radiopharmaceutical administration, scan acquisition protocols, and image reconstruction, involving technologists, physicists, and radiologists to identify bottlenecks and areas for protocol optimization and quality control enhancement. Explanation. The scenario presents a common challenge in diagnostic imaging departments: optimizing processes to improve efficiency and patient care while adhering to stringent regulatory requirements. The professional challenge lies in balancing the need for faster throughput and reduced patient waiting times with the imperative to maintain diagnostic accuracy, radiation safety, and data integrity, all within the framework of IEA standards for professional certification. Careful judgment is required to identify process improvements that are both effective and compliant. The correct approach represents best professional practice because it directly addresses the identified performance metric deviations through a systematic, evidence-based review of the entire imaging workflow. This involves engaging all relevant stakeholders, from technologists to medical physicists and radiologists, to identify root causes and implement targeted solutions. Such an approach aligns with IEA guidelines emphasizing continuous quality improvement, adherence to established protocols, and the importance of a multidisciplinary team in ensuring safe and effective diagnostic imaging services. It prioritizes patient safety and diagnostic efficacy by ensuring that any changes are validated and do not compromise the quality of the imaging or the interpretation. An incorrect approach that focuses solely on increasing scanner utilization without a comprehensive review of the imaging protocol or quality control measures is professionally unacceptable. This failure stems from a disregard for IEA principles of radiation protection and quality assurance. It risks compromising diagnostic image quality, potentially leading to misdiagnosis or the need for repeat scans, which increases patient radiation exposure and healthcare costs. Another incorrect approach that prioritizes reducing technologist time per scan without considering the impact on image acquisition parameters or patient positioning would violate the principle of obtaining diagnostically adequate images. This could lead to suboptimal image quality, impacting diagnostic accuracy, and potentially leading to increased recall rates or delayed diagnoses, which is contrary to the ethical obligation to provide high-quality patient care. A third incorrect approach that involves implementing new software without proper validation and training would be a direct contravention of IEA guidelines on the safe and effective use of medical imaging equipment and associated technologies. This could lead to system malfunctions, data loss, or incorrect image processing, all of which pose significant risks to patient safety and diagnostic integrity. The professional reasoning process for similar situations should involve a structured approach. First, clearly define the performance metric deviation and its potential impact. Second, conduct a thorough root cause analysis involving all relevant personnel and data. Third, brainstorm potential solutions, evaluating each for its effectiveness, feasibility, and compliance with IEA standards and local regulations. Fourth, prioritize and implement the most promising solutions, ensuring adequate training and validation. Finally, continuously monitor the impact of the implemented changes and be prepared to make further adjustments. This iterative process ensures that improvements are sustainable and contribute to the overall safety and quality of diagnostic imaging services. Question 2. Examination of the data shows a slight but consistent deviation in the isotopic abundance of uranium-235 in samples taken from a declared enrichment facility compared to the expected values based on initial declarations. This deviation is observed across multiple batches processed over a recent period. What is the most appropriate professional approach to address this observation? Option A. Initiate a detailed review of the facility's declared enrichment process, operational logs, and any documented changes in feedstock or equipment performance to determine if these factors can account for the observed isotopic variation. Option B. Immediately flag the deviation as indicative of undeclared enrichment activities and recommend an immediate on-site inspection to investigate potential diversion. Option C. Assume the deviation is within acceptable statistical margins of error for routine operations and require no further action unless the deviation significantly increases. Option D. Conclude that the observed isotopic abundance is a direct indicator of material unaccounted for and report it as a potential diversion without further investigation. The correct answer is A. Initiate a detailed review of the facility's declared enrichment process, operational logs, and any documented changes in feedstock or equipment performance to determine if these factors can account for the observed isotopic variation. Explanation. Scenario analysis. This scenario presents a professional challenge related to the interpretation and application of isotopic abundance data within the framework of the International Atomic Energy Agency, IAEA, safeguards. The challenge lies in discerning whether observed variations in isotopic composition of nuclear material are indicative of undeclared activities or can be explained by legitimate documented processes. Professionals must exercise careful judgment to avoid misinterpreting routine variations, which could lead to unwarranted accusations or investigations, while simultaneously ensuring that any genuine deviations from declared information are identified and addressed according to IAEA safeguards principles. The integrity of the international nonproliferation regime hinges on the accurate assessment of such data. Correct approach analysis. The correct approach involves a comprehensive review of all available information, including the declared operational history of the facility, the specific enrichment or reprocessing processes employed, and any documented changes in feedstock or operational parameters. This approach aligns with IAEA safeguards principles, which emphasize a data-driven and evidence-based assessment. By cross-referencing the observed isotopic abundance data with the facility's declared activities and operational records, a professional can determine if the variations are consistent with expected outcomes. This thorough due diligence ensures that conclusions are robust, defensible, and adhere to the spirit and letter of the IAEA safeguards agreements, particularly those related to material accountancy and the verification of declared nuclear material. Incorrect approaches analysis. Focusing solely on the observed isotopic abundance data without considering the context of declared operations is a significant regulatory and ethical failure. This approach risks misinterpreting normal process variations as anomalies, leading to unnecessary escalation and potential damage to international relations and trust. It fails to uphold the principle of a balanced and objective assessment, which is fundamental to effective safeguards implementation. Attributing observed isotopic variations to undeclared activities without a thorough investigation into potential legitimate explanations represents a premature and unsubstantiated conclusion. This is a failure of due diligence and could lead to incorrect reporting, undermining the credibility of the safeguard system. It also violates the ethical obligation to conduct a fair and impartial assessment. Assuming that any deviation from a baseline isotopic abundance, however small, automatically signifies a diversion or undeclared use of nuclear material is an overly rigid and impractical interpretation. IAEA safeguards recognize that minor fluctuations can occur due to various factors. This approach ignores the practical realities of nuclear material processing and verification, leading to an inefficient and potentially erroneous application of safeguards measures. Professional reasoning. Professionals tasked with analyzing isotopic abundance data within the IAEA safeguards framework must adopt a systematic, evidence-based, and context-aware decision-making process. This involves 1. Understanding the declared state of nuclear material and the facility's operational history. 2. Thoroughly analyzing the isotopic abundance data in conjunction with all relevant operational parameters and historical records. 3. Identifying any discrepancies between observed data and declared information. 4. Investigating potential explanations for discrepancies, prioritizing those consistent with declared activities and known scientific principles. 5. If undeclared activities are suspected, gathering further evidence and consulting with relevant experts and authorities within the IEA framework. 6. Ensuring all assessments are objective, documented, and defensible, adhering strictly to the principles of the IEA safeguards agreements. Question 3. Performance analysis shows that a portable radiation detector, used to monitor a facility handling radioisotopes, is registering a higher than expected count rate when no known source is in the immediate vicinity. Considering the fundamental principles of ionization and excitation, which of the following analytical approaches best ensures accurate assessment of the situation and adherence to professional standards for radiation monitoring? Option A. Investigating the possibility of background radiation contributing to the observed count rate by comparing readings in different locations and consulting established background radiation data for the area. Option B. Assuming all detected signals are due to ionization from an unknown source and attempting to quantify its activity based on a simplified linear relationship with the count rate. Option C. Concluding that the detector is malfunctioning and requires immediate replacement without further investigation into the nature of the detected signals. Option D. Adjusting the detector's threshold setting downwards to filter out what is assumed to be random noise, thereby reducing the observed count rate to a more acceptable level. The correct answer is D. Adjusting the detector's threshold setting downwards to filter out what is assumed to be random noise, thereby reducing the observed count rate to a more acceptable level. Explanation. Scenario analysis. This scenario presents a professional challenge in ensuring the accurate and safe interpretation of radiation detection data within the context of IEA professional certification requirements. The core difficulty lies in distinguishing between genuine ionization events caused by the intended radioactive source and spurious signals that could arise from background radiation or detector noise. Misinterpreting these signals can lead to incorrect assessments of radiation levels, potentially impacting safety protocols, operational decisions, and reporting accuracy, all of which are critical under IEA guidelines for radiation protection and nuclear safety. Professionals must exercise careful judgment to apply theoretical understanding of ionization and excitation processes to real-world detector responses. Correct approach analysis. The correct approach involves a systematic evaluation of the detector's response in relation to the expected characteristics of ionization and excitation processes induced by the specific radioactive source. This means understanding that ionization is the direct removal of an electron from an atom or molecule, leading to charged particles, while excitation is the temporary elevation of an electron to a higher energy level. A well-calibrated detector, when exposed to a known source, should exhibit a response pattern consistent with these fundamental processes. This includes considering the energy deposition characteristics of the radiation, the detector's efficiency at specific energy ranges, and the expected signal-to-noise ratio. By correlating observed signals with theoretical predictions of ionization and excitation events, professionals can confidently identify true events and differentiate them from background noise or detector artifacts, thereby upholding the integrity of their measurements and analyses as mandated by IEA standards for radiation measurement and monitoring. Incorrect approach is analysis. One incorrect approach would be to solely rely on the raw count rate from the detector without considering the underlying physical processes. This fails to account for the fact that background radiation is also causing ionization and excitation events, which will contribute to the count rate. Ignoring this fundamental aspect leads to an overestimation of the source's contribution and a potential misinterpretation of radiation levels, violating IEA principles of accurate measurement and reporting. Another incorrect approach would be to assume that any signal above a minimal threshold is directly proportional to the source's activity, without considering the detector's energy discrimination capabilities or the specific types of ionization and excitation produced by the source. Different radiation types and energies interact with detectors in distinct ways, and a simplistic assumption can lead to inaccurate conclusions about the radiation field. This neglects the detailed understanding of radiation-matter interactions required by IEA standards for effective radiation safety. A third incorrect approach would be to attribute all detected signals to ionization events, overlooking the possibility of excitation processes that might influence detector response or lead to secondary emissions. While ionization is the primary mechanism for signal generation in many detectors, a comprehensive understanding of both processes is necessary for a complete analysis, especially when dealing with complex radiation fields or advanced detector technologies. Failing to consider the full spectrum of radiation-matter interactions can lead to incomplete or misleading data interpretation, which is contrary to the rigorous scientific basis expected under IEA certification. Professional reasoning. Professionals faced with interpreting detector data should employ a decision-making framework that begins with a thorough understanding of the specific radioactive source and its expected radiation emissions. This understanding should be coupled with detailed knowledge of the radiation detector's operating principles, its calibration status, and its response characteristics to different types and energies of radiation. The next step involves comparing the observed detector response against theoretical predictions of ionization and excitation processes. This comparison should account for expected background levels and potential sources of noise. Professionals must then critically evaluate any discrepancies, seeking to explain them through a deeper understanding of the physics involved rather than making assumptions. This iterative process of theoretical prediction, empirical observation, and critical analysis ensures that conclusions drawn from the data are robust, scientifically sound, and in compliance with the stringent requirements for professional conduct and technical competence set forth by the IEA. Question 4. Risk assessment procedures indicate that a new facility is being designed for advanced nuclear energy generation. Considering the fundamental differences in their operational principles and potential safety implications, which of the following best describes the appropriate approach to assessing the risks associated with the facility's core processes? Option A. Prioritizing the assessment of potential energy output and economic viability, with safety and regulatory considerations being secondary to the primary goal of efficient power generation. Option B. Focusing the risk assessment solely on the immediate operational hazards, neglecting the long-term implications of radioactive waste management and decommissioning for both fission and fusion processes. Option C. Differentiating the risk assessment based on the specific nuclear process, fission or fusion, meticulously evaluating the unique hazards, safety systems, and regulatory considerations pertinent to each, and tailoring mitigation strategies accordingly. Option D. Applying a standardized risk assessment framework universally to all nuclear energy generation processes, assuming similar safety profiles and regulatory requirements for both fission and fusion. The correct answer is D. Applying a standardized risk assessment framework universally to all nuclear energy generation processes, assuming similar safety profiles and regulatory requirements for both fission and fusion. Explanation. Scenario analysis. This scenario presents a professional challenge due to the inherent uncertainties and potential consequences associated with advanced nuclear technologies. The distinction between fission and fusion, while fundamental, requires a nuanced understanding of their operational principles, safety implications, and regulatory oversight. Professionals must accurately assess the implications of each process for facility design, operational procedures, and emergency preparedness, ensuring that risk assessments are grounded in a thorough comprehension of the underlying physics and the specific regulatory framework of the IEA. The challenge lies in translating theoretical knowledge into practical risk management strategies that align with international safety standards. Correct approach analysis. The correct approach involves a comprehensive evaluation of the distinct characteristics of fission and fusion processes in the context of their potential impact on safety and security. This includes understanding that fission relies on the splitting of heavy atomic nuclei, a process that generates radioactive byproducts and requires robust containment and waste management strategies. Fusion, conversely, involves the merging of light atomic nuclei, a process that, while still under development for practical energy generation, is generally considered to have a more favorable safety profile regarding long-lived radioactive waste and the potential for runaway chain reactions. A professional assessment would therefore prioritize understanding how these fundamental differences influence the specific risks and the corresponding regulatory requirements for each technology, ensuring that the risk assessment accurately reflects the current state of development and the established safety principles for each. This aligns with the IEA mandate to promote the safe and secure use of nuclear technologies by providing guidance and standards that are technically sound and ethically responsible. Incorrect approaches analysis. An incorrect approach would be to treat fission and fusion as interchangeable or to apply a generic risk assessment framework without acknowledging their fundamental differences. For instance, assuming that the safety concerns and regulatory requirements for a fission reactor are directly applicable to a fusion research facility would be a significant oversight. This failure stems from a lack of deep understanding of the distinct physical processes and their associated hazards. Ethically, this could lead to inadequate safety measures for one technology while imposing unnecessary burdens on another, failing the professional duty to ensure safety and security commensurate with the specific risks. Regulatory failure would occur by not adhering to the specific guidance and standards that the IEA may have developed for each distinct technology or phase of development, potentially leading to non-compliance and increased risk. Another incorrect approach would be to focus solely on the potential energy output, without adequately considering the safety and waste management implications unique to each process, thereby misdirecting risk mitigation efforts. Professional reasoning. Professionals must adopt a systematic decision-making process that begins with a clear identification of the specific nuclear process under consideration. This is followed by a thorough review of the relevant IEA safety standards, technical documents, and guidelines pertaining to that specific process. A critical step involves dissecting the fundamental physics of the process to understand its inherent hazards and potential failure modes. This understanding then informs the development of a tailored risk assessment that considers all relevant aspects, including operational safety, radiological protection, waste management, and security. Professionals should continuously engage in learning and stay abreast of advancements in nuclear technology and evolving regulatory interpretations to ensure their risk assessments remain current and effective. This iterative process of understanding, assessing, and adapting is crucial for maintaining the highest standards of safety and security in the nuclear field. Question 5. Analysis of the potential impact of non-ionizing electromagnetic radiation (EMR) emitted by diagnostic imaging equipment within a nuclear facility on personnel and sensitive electronic systems, considering the International Atomic Energy Agency (IAEA) safety framework. Which of the following represents the most prudent and compliant approach to managing these EMR emissions? Option A. Rely on the absence of immediate, observable adverse health effects among personnel as sufficient evidence that EMR emissions are adequately controlled. Option B. Focus solely on installing extensive shielding around all diagnostic imaging equipment, as this is the most direct method of mitigating EMR exposure. Option C. Assume that non-ionizing EMR from certified diagnostic equipment poses no significant risk in a nuclear environment and therefore requires no specific management beyond standard operational procedures. Option D. Implement a comprehensive risk assessment to identify all potential EMR sources, characterize their emissions, and establish a layered system of controls including engineering solutions, administrative procedures, and appropriate personal protective equipment, guided by the ALARA principle. The correct answer is D. Implement a comprehensive risk assessment to identify all potential EMR sources, characterize their emissions, and establish a layered system of controls including engineering solutions, administrative procedures, and appropriate personal protective equipment, guided by the ALARA principle. Explanation. Scenario analysis. This scenario presents a professional challenge due to the inherent risks associated with electromagnetic radiation (EMR) in a nuclear facility. The challenge lies in balancing the operational necessity of EMR-emitting equipment with the imperative to protect personnel, the public, and the environment from potential harm. Ensuring compliance with the International Atomic Energy Agency (IAEA) safety standards, specifically those pertaining to radiation protection, and the safe use of radioactive sources and other sources of radiation, requires a nuanced understanding of EMR characteristics, exposure pathways, and effective control measures. The professional must exercise sound judgment to identify and mitigate risks, often in the face of incomplete information or competing priorities. Correct approach analysis. The correct approach emphasizes a comprehensive risk assessment and the implementation of a tiered system of protection, aligning directly with IEA principles. This involves identifying all potential sources of EMR, characterizing their emissions, and evaluating the likelihood and severity of exposure. The subsequent implementation of engineering controls, e.g., shielding, distance, administrative controls, e.g., work procedures, training, and personal protective equipment, PPE, forms a robust defense-in-depth strategy. This approach is best professional practice because it is proactive, systematic, and grounded in the ALARA, as low as reasonably achievable principle, which is a cornerstone of IEA radiation protection guidance. It ensures that all reasonable measures are taken to minimize exposure, thereby fulfilling the ethical and regulatory obligation to safeguard health and safety. Incorrect approach is analysis. One incorrect approach would be to solely rely on the absence of immediate, observable health effects. This fails to acknowledge the cumulative and long-term risks associated with EMR exposure, which may not manifest immediately. Ethically, this approach neglects the precautionary principle and the IEA emphasis on preventing harm, even in the absence of definitive proof of immediate danger. Regulatorily, it violates the requirement for systematic risk assessment and control measures. Another incorrect approach would be to assume that any EMR emitted by equipment certified for general industrial use is inherently safe and requires no further consideration. This overlooks the specific context of a nuclear facility, where background radiation levels and the presence of sensitive equipment may necessitate stricter controls. It also fails to account for potential synergistic effects or unintended consequences of EMR in a complex operational environment. This approach is ethically deficient, as it prioritizes convenience over safety and regulatorily non-compliant by not adhering to the specific safety requirements for nuclear installations. A third incorrect approach would be to focus exclusively on shielding without considering other control measures. While shielding is a critical engineering control, it may not always be feasible or sufficient. Neglecting administrative controls like access restrictions or work scheduling, or the use of appropriate PPE where necessary, creates gaps in the protection strategy. This approach is professionally unsound because it relies on a single, potentially incomplete, solution and fails to adopt a holistic, multi-layered defense strategy as advocated by IEA standards. Professional reasoning. Professionals in this domain must adopt a systematic and risk-informed decision-making process. This begins with a thorough understanding of the relevant IEA safety standards and national regulations. The process should involve 1. Hazard identification, systematically identifying all potential sources of EMR and their characteristics. 2. Risk assessment, evaluating the potential for exposure, considering the nature of the EMR, the proximity of individuals, the duration of exposure, and the effectiveness of existing controls. 3. Control measure selection, implementing a hierarchy of controls, prioritizing engineering solutions, followed by administrative controls, and finally, PPE. 4. Monitoring and review, regularly assessing the effectiveness of control measures and updating them as necessary based on operational changes or new information. This iterative process ensures continuous improvement in safety and compliance. Question 6. The risk matrix shows a potential for novel safety challenges with the introduction of small modular reactors, SMR, and Generation Roman 4, Gen Roman 4 reactor designs. Considering the International Atomic Energy Agency's, IEA, framework for nuclear safety, which of the following approaches best aligns with ensuring the safe and secure deployment of these advanced reactor technologies? Option A. Expediting the licensing and deployment process for SMRs and Gen Roman 4 reactors by applying a streamlined regulatory review that assumes inherent safety due to their advanced nature, minimizing upfront safety analysis. Option B. Prioritizing a comprehensive, risk-informed, and performance-based safety assessment that is tailored to the specific design features and operational characteristics of SMRs and Gen Roman 4 reactors, ensuring alignment with IEA safety standards and principles. Option C. Relying primarily on the extensive operational history and established regulatory precedents of large-scale, traditional nuclear power plants, assuming similar safety performance for SMRs and Gen Roman 4 designs. Option D. Adopting a generic safety assessment methodology that applies uniform safety criteria across all reactor types, without specific consideration for the unique technological advancements and potential new safety considerations introduced by SMRs and Gen Roman 4 designs? The correct answer is B. Prioritizing a comprehensive, risk-informed, and performance-based safety assessment that is tailored to the specific design features and operational characteristics of SMRs and Gen Roman 4 reactors, ensuring alignment with IAEA safety standards and principles. Explanation: the scenario presents a professional challenge in evaluating the safety and regulatory implications of advanced reactor designs, specifically small modular reactors, SMR, and Generation Roman 4, Gen Roman 4, reactors, within the framework of the International Atomic Energy Agency, IAEA standards and guidelines. The challenge lies in discerning which approach to safety assessment and regulatory oversight is most aligned with the IAEA principles for ensuring nuclear safety, security, and safeguards, particularly when these advanced designs may introduce novel safety features or operational paradigms compared to traditional large-scale reactors. Careful judgment is required to distinguish between approaches that proactively address potential new risks and those that might inadvertently overlook them or apply outdated regulatory perspectives. The correct approach represents best professional practice because it emphasizes a comprehensive, risk-informed, and performance-based evaluation that is central to the IAEA safety standards. This approach acknowledges that while SMRs and Gen Roman 4 reactors aim for enhanced safety, their unique characteristics necessitate a tailored regulatory framework. It involves a thorough understanding of the specific design features, potential accident scenarios, and the effectiveness of proposed safety systems, all assessed against the overarching safety objectives and principles articulated in IAEA Safety Standards Series publication. This aligns with the IAEA mandate to promote the safe and secure use of nuclear technology globally, ensuring that new designs meet or exceed established safety benchmarks. An incorrect approach that focuses solely on historical operational data from conventional reactors fails to acknowledge the fundamental differences in design, scale, and potential failure modes of SMRs and Gen Roman 4 reactors. This represents a regulatory failure by not adequately considering the unique safety aspects of these advanced technologies, potentially leading to an underestimation of risks or an inappropriate application of existing regulations. Another incorrect approach that prioritizes rapid deployment without a commensurate rigorous safety review and regulatory approval process is ethically and regulatorily unsound. This approach risks compromising nuclear safety and security by prioritizing expediency over thoroughness, violating the core principles of responsible nuclear development promoted by the IAEA. A third incorrect approach that relies on generic safety assumptions without a detailed, design-specific analysis would also be professionally unacceptable. This overlooks the critical need for a nuanced understanding of how specific design choices in SMRs and Gen Roman 4 reactors influence their safety performance, potentially leading to inadequate safety margins or ineffective regulatory oversight. The professional decision-making process for similar situations should involve a systematic evaluation of the proposed technology against established IAEA safety principles and guidelines. This includes 1. Understanding the specific design and its intended operational context. 2. Identifying novel safety features and potential new risks. 3. Conducting a risk-informed and performance-based assessment of these risks. 4. Ensuring that regulatory frameworks are adapted or developed to adequately address the unique characteristics of the advanced design. And 5. Maintaining a commitment to continuous improvement and learning throughout the life cycle of the technology. Question 7. The performance metrics show a sustained, low-level increase in gamma radiation readings from a portable survey meter in an area typically characterized by stable background levels. The instrument's self-test diagnostics indicate it is functioning within its specified parameters. Considering the principles of radiation physics and the instrument's capabilities, what is the most prudent initial course of action? Option A. Immediately recalibrate the instrument, assuming the readings are indicative of a calibration drift despite the self-test results. Option B. Disregard the readings as likely due to minor environmental fluctuations that the instrument's self-test cannot fully account for. Option C. Conduct a systematic search for potential localized sources of radioactive material in the vicinity, considering the type of radiation the instrument is sensitive to and potential pathways for contamination. Option D. Report the instrument for immediate decommissioning and replacement due to suspected internal component degradation, affecting sensitivity. The correct answer is C. Conduct a systematic search for potential localized sources of radioactive material in the vicinity, considering the type of radiation the instrument is sensitive to and potential pathways for contamination. Explanation: scenario analysis. This scenario is professionally challenging because it requires the application of fundamental radiation physics principles to interpret real-world performance data from a radiation monitoring instrument. The challenge lies in distinguishing between a genuine instrument malfunction and a legitimate, albeit unusual, radiation event. Misinterpreting the data could lead to either unnecessary alarm and resource diversion or, more critically, a failure to detect a real radiological hazard, potentially compromising safety and security. The professional must exercise sound judgment based on their understanding of radiation physics and the instrument's operational characteristics. Correct approach analysis. The correct approach involves a systematic evaluation of the observed radiation readings in the context of known radiation physics and the instrument's specifications. This includes considering the type of radiation the instrument is designed to detect, its sensitivity, potential sources of background radiation, and the expected behavior of radiation fields under normal and abnormal conditions. By comparing the anomalous readings to expected background levels and considering potential physical explanations for elevated readings, e.g., presence of a radioactive source, changes in shielding, instrument self-test anomalies, the professional can make an informed decision. This aligns with IEA safety standards and professional certification requirements, which emphasize a thorough, evidence-based approach to radiation safety and monitoring. The principle of defense in depth also supports this methodical evaluation, ensuring that potential hazards are not overlooked due to hasty conclusions. Incorrect approaches analysis. One incorrect approach is to immediately assume a malfunction without considering physical explanations. This fails to acknowledge the possibility of a genuine radiation event and could lead to a delayed or missed response to a safety or security concern. Ethically and regulatorily, this represents a failure to exercise due diligence in radiation protection. Another incorrect approach is to attribute the elevated readings solely to environmental factors without a deeper understanding of radiation physics. While environmental factors can influence readings, a superficial assessment might overlook specific radioactive sources or phenomena that require investigation. This approach lacks the depth of analysis required by professional standards and could lead to an incomplete or inaccurate assessment of the situation. A third incorrect approach is to rely on anecdotal evidence or past experiences with similar instruments without a rigorous, data-driven analysis. While experience is valuable, each situation must be assessed on its own merits, considering the specific physics of the observed readings and the instrument's current operational state. This approach risks confirmation bias and can lead to overlooking critical details, which is a failure in professional responsibility. Professional reasoning. Professionals should adopt a structured decision-making process. 1. Understand the instrument's operational principles and limitations in relation to radiation physics. 2. Analyze the anomalous data in the context of expected background radiation and potential physical phenomena. 3. Consult instrument calibration records and maintenance logs. 4. Consider potential sources of radiation relevant to the operational environment. 5. If necessary, employ complementary monitoring techniques or consult with subject matter experts. 6. Document all observations, analyses, and decisions thoroughly. This systematic approach ensures that decisions are based on sound scientific principles and regulatory requirements, prioritizing safety and security. Question 8. Research into optimizing the physical protection systems for a facility handling significant quantities of Category I nuclear material has identified several potential approaches. Which approach best aligns with the principles of effective and sustainable nuclear security? Option A. Establishing the physical protection system once and conducting only infrequent scheduled reviews to ensure its continued operation. Option B. Adhering strictly to the minimum security requirements stipulated by national regulations, with no additional measures considered unless explicitly mandated. Option C. Implementing a comprehensive, risk-informed, and performance-based strategy that continuously adapts to evolving threats and technological advancements. Option D. Prioritizing the acquisition and deployment of the most technologically advanced security systems available, regardless of specific threat assessments or cost-benefit analyses. The correct answer is C. implementing a comprehensive, risk-informed, and performance-based strategy that continuously adapts to evolving threats and technological advancements. Explanation: scenario analysis. This scenario presents a professional challenge in optimizing physical protection systems for nuclear materials. The challenge lies in balancing the imperative of robust security against the practicalities of resource allocation, operational efficiency, and the evolving threat landscape. Professionals must exercise careful judgment to ensure that security measures are effective, sustainable, and proportionate to the risks without unduly hindering legitimate operations or incurring excessive costs. The dynamic nature of threats and technological advancements necessitates a continuous review and adaptation of protection strategies. Correct approach analysis. The correct approach involves a comprehensive, risk-informed, and performance-based strategy. This methodology prioritizes security measures based on a thorough assessment of potential threats, vulnerabilities, and the consequences of a security event. It emphasizes achieving specific security outcomes rather than rigidly adhering to prescriptive measures. This aligns with the International Atomic Energy Agency (IAEA) principles for the physical protection of nuclear material and nuclear facilities, which advocate for a flexible and adaptable approach that can be tailored to specific national contexts and threat environments. A performance-based approach allows for innovation and the integration of new technologies, ensuring that protection systems remain effective and efficient over time. It also promotes a culture of continuous improvement, essential for maintaining a high level of security. Incorrect approaches analysis. Focusing solely on the most advanced and expensive technologies without a commensurate risk assessment represents a failure to adhere to the principle of proportionality. This approach can lead to inefficient resource allocation, potentially diverting funds from other critical security areas or operational needs. It also risks creating a system that is overly complex and difficult to maintain, thereby increasing the likelihood of operational failures. Ethically, it may be seen as a misallocation of resources that could be better utilized elsewhere if the risk does not warrant such an extreme level of investment. Implementing only the minimum legally mandated security measures, without considering the specific threat profile or potential vulnerabilities of the facility, is a significant regulatory and ethical failure. While compliance with regulations is essential, it does not guarantee adequate protection. This approach neglects the dynamic nature of threats and the responsibility to proactively safeguard nuclear materials. It demonstrates a lack of due diligence and a failure to exercise professional judgment in ensuring the highest possible level of security. This could lead to a security posture that is insufficient to deter or respond effectively to a determined adversary. Adopting a set-it-and-forget-it mentality, where physical protection systems are implemented and then rarely reviewed or updated, is professionally unacceptable. This approach ignores the evolving threat landscape, technological advancements, and potential degradation of security components over time. It represents a failure to maintain the effectiveness of the protection system and a disregard for the continuous improvement principles advocated by international best practices. This can lead to a false sense of security and leave the facility vulnerable to emerging threats or unforeseen weaknesses. Professional reasoning. Professionals responsible for physical protection systems must adopt a systematic and iterative process. This begins with a thorough threat and vulnerability assessment, followed by the development of a security strategy that is risk-informed and performance-based. Regular reviews, drills, and exercises are crucial to test the effectiveness of the systems and identify areas for improvement. Collaboration with national authorities and adherence to international standards, such as those provided by the IAEA, are paramount. Decision-making should be guided by a commitment to the highest standards of safety and security, ensuring that all measures are proportionate to the identified risks and contribute to the overall security posture of the facility. Question 9. The control framework reveals that a newly commissioned nuclear power plant is experiencing minor, intermittent deviations from its established operational parameters, occurring with increasing frequency. Which of the following actions best upholds the principles of nuclear safety and professional responsibility? Option A. Temporarily suspend operations for a thorough, unscheduled inspection of all plant systems to identify and rectify any potential problems, regardless of the severity of the deviations. Option B. Initiate a comprehensive root cause analysis involving relevant experts to identify the underlying issues and develop a corrective action plan, while continuing operations under enhanced monitoring. Option C. Document the deviations and instruct operators to monitor them closely, assuming they are minor and will self-correct over time. Option D. Rely on the experience of senior operators to assess the deviations and implement informal adjustments to operational procedures as needed. The correct answer is B. Initiate a comprehensive root cause analysis involving relevant experts to identify the underlying issues and develop a corrective action plan, while continuing operations under enhanced monitoring. Explanation. The control framework reveals a situation where a newly commissioned nuclear power plant is experiencing minor, intermittent deviations from its established operational parameters. These deviations, while not immediately posing a safety threat, are occurring with increasing frequency. The challenge lies in balancing the need for continued power generation with the paramount principle of nuclear safety, which demands proactive identification and mitigation of potential risks. A hasty decision to ignore or downplay these deviations could lead to a more significant safety event, while an overly cautious approach might unnecessarily disrupt operations and incur substantial economic losses. The correct approach involves a systematic, evidence-based investigation that prioritizes safety. This means immediately initiating a thorough root cause analysis, RCA, of the deviations, involving experienced nuclear safety engineers and operators. The RCA should meticulously examine all relevant systems, procedures, and human factors. Based on the findings, a robust corrective action plan must be developed and implemented, with continuous monitoring to ensure its effectiveness. This approach aligns with the fundamental principles of nuclear safety, emphasizing defense in depth, safety culture, and the ALARA, as low as reasonably achievable principle for radiation exposure, by proactively addressing potential issues before they escalate. It also adheres to the IAEA safety standards, which stress the importance of a strong safety culture and continuous improvement. An incorrect approach would be to attribute the deviations to minor, transient issues without a formal investigation, hoping they will resolve themselves. This demonstrates a failure in safety culture and a disregard for the principle of defense in depth, as it neglects potential underlying systemic problems. Another incorrect approach would be to immediately shut down the plant for an extensive, unscheduled overhaul based on insufficient evidence. While seemingly cautious, this lacks proportionality and could be economically damaging without a clear safety imperative, failing to apply sound professional judgment, and potentially violating principles of efficient resource management within the regulatory framework. A third incorrect approach would be to rely solely on operator intuition without engaging formal engineering analysis, which undermines the systematic and rigorous approach required for nuclear safety and could lead to misdiagnosis of the problem. Professional decision-making in such scenarios requires a structured process. First, acknowledge and document the deviations. Second, initiate a formal investigation process, engaging the appropriate expertise. Third, analyze the data and evidence to determine the root cause. Fourth, develop and implement a proportionate and effective corrective action plan. Fifth, monitor the effectiveness of the corrective actions and reassess as necessary. This systematic approach ensures that decisions are grounded in facts, prioritize safety, and are defensible within the regulatory framework. Question 10. The risk matrix shows a moderate probability of unexpected secondary radiation emissions when a novel shielding material is subjected to high-energy particle bombardment, but the exact nature and energy spectrum of these emissions are not fully characterized. A research team proposes to proceed with further testing of the material's effectiveness in a controlled laboratory environment, citing the potential for significant advancements in radiation protection technology. What is the most ethically and professionally responsible course of action? Option A. Conduct extensive experimental characterization of the secondary emissions under various bombardment conditions, perform a comprehensive risk assessment based on this data, and develop specific mitigation strategies before proceeding with further testing. Option B. Proceed with the proposed laboratory testing, assuming the secondary emissions will be within acceptable safety limits based on initial theoretical predictions, and monitor for any anomalies. Option C. Focus solely on the primary objective of testing the material's shielding effectiveness, treating any secondary emissions as a secondary concern to be addressed only if they become a significant problem. Option D. Halt all further research on the novel shielding material until a complete theoretical understanding of all possible radiation interactions is achieved, even if it means delaying potential safety advancements. The correct answer is A. Conduct extensive experimental characterization of the secondary emissions under various bombardment conditions, perform a comprehensive risk assessment based on this data, and develop specific mitigation strategies before proceeding with further testing. Explanation. This scenario presents a professional challenge due to the inherent uncertainty in predicting the precise interaction of radiation with matter, especially when dealing with novel or complex materials. The ethical dilemma arises from balancing the pursuit of scientific advancement with the paramount responsibility to ensure safety and prevent unintended harm. Careful judgment is required to interpret incomplete data and make decisions that protect both personnel and the environment. The correct approach represents best professional practice because it prioritizes a thorough, evidence-based understanding of the radiation-matter interaction before proceeding with potentially hazardous applications. This aligns with the fundamental principles of radiation safety and the IAEA emphasis on a robust safety culture. Specifically, it adheres to the precautionary principle, which dictates that where there are threats of serious or irreversible damage, lack of full scientific certainty shall not be used as a reason for postponing cost-effective measures to prevent environmental degradation or harm to human health. This approach involves rigorous experimental validation, comprehensive risk assessment, and consultation with experts, ensuring that all potential consequences are considered and mitigated according to established IAEA safety standards and guidelines. An incorrect approach that relies solely on theoretical models without experimental verification fails to acknowledge the complexities and potential deviations in real-world interactions. This represents a regulatory and ethical failure by not adequately assessing risks, potentially leading to unforeseen exposures or contamination. Another incorrect approach that proceeds with the application despite significant uncertainties, hoping for the best, demonstrates a disregard for the safety culture and the principle of ALARA as low as reasonably achievable for radiation exposure. This is a direct ethical and regulatory failure, as it prioritizes expediency over safety and fails to uphold the IAEA mandate for responsible nuclear technology use. A third incorrect approach that dismisses the need for further investigation due to perceived minor deviations from expected outcomes ignores the potential for cumulative or cascading effects, a significant ethical and regulatory lapse in due diligence. A professional decision-making process for similar situations should involve a systematic evaluation of available data, a clear understanding of the relevant IAEA safety standards and guidance documents, and a commitment to a conservative approach when uncertainties exist. Professionals should actively seek diverse expert opinions, conduct thorough risk assessments that consider worst-case scenarios, and implement robust monitoring and control measures. Transparency and clear communication of risks and uncertainties to all stakeholders are also crucial components of ethical and professional conduct. Question 11. Which approach would be most effective in demonstrating a candidate's understanding of conservation laws in nuclear reactions for the International Atomic Energy Agency professional certifications? Option A. Focusing on the complex mathematical models used to calculate the probability of specific nuclear reactions occurring. Option B. Explaining how conservation of mass energy, momentum, charge, baryon number, and lepton number dictates the outcomes and feasibility of various nuclear reactions, such as fission, fusion, and decay. Option C. Describing the engineering designs of nuclear reactors that exploit nuclear reactions without explicitly referencing the governing conservation principles. Option D. Detailing the historical timeline of discoveries that led to the formulation of conservation laws in nuclear physics. The correct answer is B. Explaining how conservation of mass energy, momentum, charge, baryon number, and lepton number dictates the outcomes and feasibility of various nuclear reactions, such as fission, fusion, and decay. Explanation. Scenario analysis. This scenario is professionally challenging because it requires an individual to apply fundamental physics principles, specifically conservation laws in nuclear reactions, within the strict confines of the International Atomic Energy Agency, IAEA, regulatory framework for professional certifications. The challenge lies in identifying the correct conceptual understanding of these laws as they pertain to nuclear processes, and how this understanding is assessed in a certification context, rather than performing calculations. Professionals must demonstrate not just knowledge of the physics, but also the ability to interpret and apply it in a manner consistent with the IEA standards for competence. Correct approach analysis. The correct approach represents best professional practice because it directly assesses the candidate's understanding of the theoretical underpinnings of nuclear reactions as mandated by the IEA certification program. Conservation laws, mass energy, momentum, charge, baryon number, lepton number, are foundational to understanding nuclear processes, from fission and fusion to radioactive decay. Professionals certified by the IEA must be able to articulate how these laws govern nuclear transformations, ensuring safety, predictability, and responsible management of nuclear materials and technologies. This approach aligns with the IEA objective of promoting safe, secure, and peaceful uses of nuclear science and technology by verifying that certified professionals possess a robust theoretical grasp of the phenomena they will be involved with. Incorrect approach is analysis, an approach that focuses solely on the historical development of nuclear physics without emphasizing the application of conservation laws would be professionally unacceptable. While historical context is valuable, IEA certifications are concerned with current scientific understanding and its practical implications for nuclear safety and security. This approach fails to demonstrate the required competency in applying fundamental principles. Another incorrect approach would be one that delves into the detailed mathematical derivations of nuclear reaction cross-sections. While mathematics is integral to nuclear physics, the IEA certification for professionals often emphasizes conceptual understanding and the implications of these laws rather than advanced computational skills, unless the certification specifically targets a highly specialized computational role. This approach might be too narrowly focused on calculation and miss the broader conceptual grasp of conservation principles. Finally, an approach that discusses the engineering applications of nuclear reaction without grounding it in the underlying conservation laws would also be professionally deficient. While engineering applications are crucial, a fundamental understanding of the physics, particularly conservation laws, is the bedrock upon which safe and effective engineering designs are built. Without this foundation, the understanding of the applications would be superficial and potentially lead to misjudgments in safety-critical situations. Professional reasoning. Professionals facing similar situations should first identify the core competencies and knowledge domains required by the specific certification. They should then analyze how fundamental scientific principles, such as conservation laws, are integrated into the assessment criteria. The decision-making process involves prioritizing approaches that demonstrate a deep conceptual understanding and the ability to apply these principles within the regulatory context of the IEA, rather than focusing on peripheral knowledge or overly specialized computational aspects, unless explicitly required. This ensures that the preparation and demonstration of knowledge are directly aligned with the certification's objectives for ensuring competent professionals in the nuclear field. Question 12. The review process indicates that while individual safety systems within a nuclear facility are functioning as designed, there is a lack of documented analysis demonstrating the effectiveness of the combined, independent layers of protection against a common cause failure scenario. Which of the following approaches best addresses this deficiency in accordance with the principles of defense in depth? Option A. Implement additional redundant safety systems that are physically and functionally independent of existing systems without re-evaluating the overall defense in depth strategy. Option B. Rely on the historical operational record of the facility, which shows no significant incidents, as evidence that the current defense in depth strategy is adequate. Option C. Focus on enhancing the reliability of the most critical individual safety systems, assuming that strengthening these will inherently improve the overall defense in depth. Option D. Conduct a comprehensive probabilistic safety assessment, PSA, that explicitly models the interactions between different safety layers and evaluates the impact of common cause failures on the overall safety goals. The correct answer is D. Conduct a comprehensive probabilistic safety assessment, PSA, that explicitly models the interactions between different safety layers and evaluates the impact of common cause failures on the overall safety goals. Explanation. The review process indicates a potential gap in the implementation of a defense-in-depth strategy for a nuclear facility. This scenario is professionally challenging because it requires a nuanced understanding of how multiple, independent layers of protection interact to prevent or mitigate accidents. The effectiveness of defense in depth relies not just on the presence of each layer, but on their synergistic performance and the robustness of the systems designed to detect, control, and mitigate deviations from normal operation. A failure to adequately assess the combined effectiveness of these layers can lead to an underestimation of residual risk. The correct approach represents best professional practice because it directly addresses the core principle of defense in depth, ensuring that no single failure can lead to a severe accident. This involves a comprehensive assessment of how each barrier, system, and procedural control contributes to overall safety and how their failure modes might cascade. It necessitates evaluating the independence of these layers, the effectiveness of detection and warning systems, and the capacity of mitigation systems to function even under degraded conditions. Adherence to IAEA safety standards, particularly those related to nuclear safety and defense in depth, is paramount. This approach ensures that the facility's safety case is robust and that potential vulnerabilities are identified and addressed proactively, aligning with the ethical obligation to protect public health and the environment. An incorrect approach that focuses solely on the functionality of individual safety systems without considering their interdependencies and the potential for common cause failures would be professionally unacceptable. This failure stems from a superficial understanding of defense in depth, which is more than just a collection of safety features. It's an integrated strategy. Such an approach could lead to a false sense of security, as a single event or failure mode could compromise multiple layers simultaneously, violating the principle of redundancy and diversity. Another incorrect approach that prioritizes operational efficiency or cost reduction over a thorough defense in depth assessment would be a significant regulatory and ethical failure. This demonstrates a disregard for the fundamental safety culture required in nuclear operations and a potential violation of the IAEA safety fundamentals, which emphasize the paramount importance of safety. It prioritizes economic considerations over the protection of human life and the environment, which is ethically indefensible and likely contravenes national regulatory frameworks that are based on international best practices. A professional reasoning process for such situations involves a systematic evaluation of the safety case against established principles and regulatory requirements. This includes 1. Understanding the facility's design basis and operational context. 2. Identifying all layers of defense, from physical barriers to operational procedures and emergency preparedness. 3. Analyzing the failure modes and effects of each layer and their potential interactions. 4. Assessing the effectiveness of detection, control, and mitigation systems under various accident scenarios. 5. Comparing the findings against IAEA safety standards and national regulations. 6. Documenting the assessment and proposing corrective actions for any identified deficiencies. This structured approach ensures that all aspects of defense in depth are considered, leading to informed decisions that uphold the highest safety standards. Question 13. The analysis reveals that a state operating a newly commissioned uranium enrichment facility is considering implementing a novel cascade configuration designed to significantly increase output efficiency. However, preliminary assessments indicate that this new configuration might introduce complexities in real-time material accounting and potentially obscure the precise measurement of declared versus undeclared enrichment activities, even though the state asserts its unwavering commitment to peaceful uses and full transparency. The facility manager is tasked with deciding how to proceed with the implementation of this new configuration. Option A. Proceed with the implementation of the new cascade configuration, but implement enhanced internal security measures to prevent any potential diversion, and only inform the IAEA if specific discrepancies are detected during routine monitoring. Option B. Proceed with the implementation of the new cascade configuration, ensuring that all enrichment activities are meticulously documented and reported to the IAEA, and proactively engaging with IAEA inspectors to explain the technical changes and facilitate verification of the new system. Option C. Implement the new cascade configuration immediately to maximize efficiency, assuming that the IAEA existing verification methodologies will be sufficient to detect any anomalies, and deferring detailed discussions about the configuration's impact on accounting until a later date. Option D. Halt the implementation of the new cascade configuration and revert to the previous, less efficient but fully understood and verified system, prioritizing absolute certainty in safeguards compliance over potential efficiency gains. The correct answer is B. Proceed with the implementation of the new cascade configuration, ensuring that all enrichment activities are meticulously documented and reported to the IEA, and proactively engaging with IEA inspectors to explain the technical changes and facilitate verification of the new system. Explanation. This scenario presents a professional challenge due to the inherent dual-use nature of enrichment technologies and the stringent international safeguards regime designed to prevent proliferation. The decision-maker must balance the legitimate need for nuclear material for peaceful purposes with the imperative to uphold global security and prevent diversion for illicit weapons programs. This requires a deep understanding of IEA safeguards, specific enrichment technologies, and the legal and ethical obligations of states and individuals involved. The correct approach represents best professional practice because it prioritizes adherence to the IEA statute and the comprehensive safeguard system. This includes meticulous record-keeping, transparent reporting of all enrichment activities, and proactive engagement with IEA inspectors. Such an approach ensures that all enrichment processes are conducted in accordance with Article Roman III of the IEA statute, which mandates that IEA activities be carried out for the benefit of all members of the agency and in compliance with their respective national policies, and international standards and International Atomic Energy Agency regulations. It also aligns with the spirit and letter of safeguards agreements, such as the Model Additional Protocol, which requires states to provide the IEA with additional information and access to facilities and other locations to verify the peaceful use of nuclear material. An incorrect approach that focuses solely on the technical efficiency of the enrichment process without adequate consideration for safeguards would represent a significant regulatory and ethical failure. This would violate the fundamental principle of non-proliferation enshrined in international treaties and IEA safeguards agreements. Such a failure could lead to the undetected diversion of enriched material, thereby undermining global security and potentially triggering severe international repercussions for the state and individuals involved. Another incorrect approach, which involves withholding or misrepresenting information about enrichment activities to the IEA, constitutes a direct breach of legal obligations under safeguards agreements. This is not only a regulatory violation, but also an ethical lapse, as it undermines the trust and transparency essential for the international safeguard system to function effectively. Such actions could be interpreted as attempts to conceal noncompliance, leading to the imposition of sanctions and the loss of international confidence. A third incorrect approach, which might involve prioritizing national economic interests over strict adherence to safeguard, is also professionally unacceptable. While states have sovereign rights to develop nuclear energy for peaceful purposes, these rights are intrinsically linked to the obligation to comply with international safeguards. Economic considerations cannot supersede the paramount importance of preventing nuclear proliferation. The professional decision-making process for similar situations should involve a systematic evaluation of all actions against the requirements of the IEA statute, relevant safeguards agreements, and the additional protocol. Professionals must cultivate a culture of compliance, ensuring that all personnel involved in enrichment activities are fully aware of their responsibilities and the potential consequences of non-compliance. Regular training, clear internal procedures, and open communication channels with the IEA are crucial elements of this process. Question 14. The performance metrics show a facility's radioactive contamination levels and potential radiation exposure rates. Which approach best reflects the accurate and professional application of IEA measurement units for communicating these findings to regulatory bodies and facility personnel? Option A. Reporting all radiation measurements, including contamination and exposure, solely in Becquerel BQ to simplify communication. Option B. Presenting contamination levels as equivalent dose rates in sievert SV per unit area and exposure rates as absorbed dose in gray Gi. Option C. Using gray Gi to describe both the energy deposited by radiation and the potential biological harm to individuals. Option D. Clearly stating contamination in Becquerel BQ per unit area, absorbed dose rates in gray Gi per hour, and potential health risks in sievert SV per year, ensuring each unit accurately represents its defined physical quantity. The correct answer is D. Clearly stating contamination in Becquerel BQ per unit area, absorbed dose rates in gray Gi per hour, and potential health risks in sievert SV per year, ensuring each unit accurately represents its defined physical quantity. Explanation. Scenario analysis. This scenario presents a professional challenge in accurately interpreting and communicating radiation measurement units within the context of IEA standards. The challenge lies in ensuring that stakeholders, who may have varying levels of technical expertise, understand the implications of radiation exposure and contamination levels. Misinterpreting or misapplying units like Becquerel BQ, Gray JI, and Sievert SV can lead to incorrect risk assessments, inappropriate safety measures, and potential noncompliance with IEA safety standards and guidance documents. The professional must demonstrate a clear understanding of the distinct physical quantities each unit represents and their relevance in different contexts of radiation protection. Correct approach analysis. The correct approach involves clearly distinguishing between activity Becquerel, absorbed dose Gray, and equivalent dose/effective dose Sievert. Becquerel quantifies the rate of radioactive decay of a radionuclide, indicating the amount of radioactive material present. Gray measures the energy deposited per unit mass of material, representing the physical interaction of radiation with matter. Sievert quantifies the biological risk by accounting for the type of radiation and the sensitivity of the tissue, providing a measure relevant for health protection. Professional who correctly applies these units ensures that communication regarding radioactive contamination, radiation fields, and potential health risks is precise, scientifically sound, and aligned with IEA principles for radiation safety and protection. This precision is fundamental to informed decision-making in radiation safety management. Incorrect approaches analysis. Confusing Becquerel with Sievert represents a significant regulatory and ethical failure. Becquerel measures the number of decays per second, which is a measure of radioactivity, not the biological harm. Sievert, on the other hand, is a measure of biological risk, equivalent dose or effective dose. Using BQ to describe health risk is scientifically inaccurate and can lead to underestimation or overestimation of the danger, potentially resulting in inadequate protective measures or unnecessary alarm. Equating Gray with Sievert is another regulatory and ethical failure. Gray measures the absorbed dose. It does not account for the biological effectiveness of different types of radiation or the varying sensitivity of different tissues. Sievert incorporates these factors through radiation weighting factors and tissue weighting factors, making it the appropriate unit for assessing stochastic health effects and setting dose limits for radiation protection. Using Gray alone for health risk assessment would be incomplete and misleading. Using Becquerel to represent absorbed dose is a fundamental misunderstanding of the physical quantities. Becquerel relates to the rate of nuclear transformations, while Gray relates to the energy deposited. They measure entirely different phenomena, and their interchangeability would render any safety assessment or communication meaningless and non-compliant with IEA standards for radiation measurement and protection. Professional reasoning. Professionals in the nuclear field must adopt a rigorous approach to unit selection and application. This involves a thorough understanding of the IEA safety fundamentals and radiation protection and safety of radioactive sources, international basic safety standards for protection against ionizing radiation, and for the safety of radiation sources, IEA Safety Standards Series No. GSR Part 3. When presented with performance metrics, the professional should first identify the physical quantity being measured or assessed. If the metric relates to the rate of radioactive decay, Becquerel is appropriate. If it concerns energy deposition in matter, Gray is the unit. For assessing biological risk and setting dose limits, Sievert is essential. The decision-making process should prioritize clarity, accuracy, and adherence to international standards to ensure effective radiation safety and protection for individuals and the environment. Question 15. Quality control measures reveal that the current risk assessment methodology employed at a nuclear power plant, while effective in identifying operational hazards, does not adequately address the potential for cascading failures or the integration of security-related risks. The plant is regulated under the International Atomic Energy Agency (IAEA) framework. Which of the following actions best represents the appropriate response to this finding? Ensuring compliance with IAEA guidelines and best practices for nuclear safety and security. Option A. Implement a new risk assessment methodology that is specifically designed for the nuclear industry and has been recognized or recommended by the IAEA for its comprehensive approach to safety and security, including the analysis of complex failure scenarios. Option B. Enhance the existing methodology by adding a supplementary checklist for security threats, relying primarily on the current qualitative assessment for operational hazards. Option C. Adopt a widely used risk assessment framework from another highly regulated industry, such as aviation, and adapt its terminology to fit the nuclear context. Option D. Conduct a series of workshops with senior management to discuss the perceived importance of integrating security risks without immediately altering the established risk assessment process. The correct answer is A. Implement a new risk assessment methodology that is specifically designed for the nuclear industry and has been recognized or recommended by the IAEA for its comprehensive approach to safety and security, including the analysis of complex failure scenarios. Explanation: Scenario analysis. This scenario presents a professional challenge because the implementation of a new risk assessment methodology within an IAEA-regulated facility requires not only technical understanding, but also adherence to the specific regulatory framework governing nuclear safety and security. The challenge lies in selecting and applying a methodology that is both effective in identifying and evaluating risks and compliant with IAEA standards and guidelines. Professionals must exercise careful judgment to ensure that the chosen approach aligns with the overarching safety culture and regulatory expectations, preventing potential oversights that could compromise safety or security. Correct approach analysis. The correct approach involves selecting a risk assessment methodology that is explicitly recognized or recommended by the IAEA for use in nuclear facilities. This ensures alignment with international best practices and regulatory expectations. Such methodologies are typically well documented, have undergone peer review, and are designed to address the unique complexities of nuclear operations, including the potential for severe accidents and security threats. Adhering to IAEA guidance demonstrates a commitment to a robust safety culture and regulatory compliance, which is paramount in the nuclear industry. This approach prioritizes a systematic, comprehensive, and internationally validated framework for risk identification, analysis, and mitigation. Incorrect approach is analysis. An incorrect approach would be to adopt a risk assessment methodology that is not aligned with IAEA standards or is primarily designed for non-nuclear industries without thorough adaptation and validation for the nuclear context. For instance, using a generic qualitative risk matrix without considering the specific probabilistic safety assessment (PSA) requirements or the potential for common cause failures, as emphasized by IAEA safety standards, would be a regulatory failure. Another failure would be to rely solely on expert judgment without a structured, documented process that can be audited and reviewed, as IAEA guidelines promote transparency and traceability in risk assessment. Furthermore, choosing a methodology that does not adequately address both safety and security risks, or one that is overly simplistic and fails to capture the nuances of nuclear hazards, would represent an ethical and professional lapse, potentially leading to inadequate risk management and compromised safety. Professional reasoning. Professionals in IAEA-regulated facilities must adopt a decision-making process that prioritizes regulatory compliance and international best practices. This involves 1. Identifying relevant IAEA safety standards, guides, and technical documents pertaining to risk assessment. 2. Evaluating available methodologies against these IAEA requirements, considering their scope, depth, and applicability to the specific facility and its operations. 3. Consulting with subject matter experts and regulatory bodies to ensure the chosen methodology is appropriate and will be accepted. 4. Implementing the chosen methodology with rigorous documentation, validation, and periodic review to ensure its continued effectiveness and compliance. 5. Fostering a culture where risk assessment is an integral part of all operational and design decisions, not merely a compliance exercise. Question 16. During the evaluation of a sample suspected to be a source of ionizing radiation, a technician incorrectly assumes that all isotopes of a given element will exhibit identical radiological hazards and require the same regulatory controls, solely based on the element's atomic number. Which of the following best describes the fundamental flaw in this reasoning from a nuclear regulatory perspective? Option A. The technician failed to recognize that atomic mass, which accounts for the number of neutrons, is critical for distinguishing isotopes and their unique radiological properties, a key factor in regulatory classification. Option B. The technician incorrectly equated atomic mass with atomic number, leading to a misidentification of the element itself. Option C. The technician correctly focused on the atomic number as the sole determinant of an element's regulatory significance, as chemical behavior dictates all safety protocols. Option D. The technician's assumption that all isotopes of an element have identical radiological properties is a correct interpretation of basic nuclear physics principles. Correct answer is A. The technician failed to recognize that atomic mass, which accounts for the number of neutrons, is critical for distinguishing isotopes and their unique radiological properties, a key factor in regulatory classification. Explanation: scenario analysis. This scenario presents a professional challenge in accurately identifying and classifying radioactive materials based on their fundamental nuclear properties. Misidentification can lead to incorrect safety protocols, improper waste management, and potential regulatory noncompliance, all of which have significant implications for nuclear safety and security. The challenge lies in distinguishing between isotopes of the same element, which share the same atomic number but differ in atomic mass due to varying neutron counts, and understanding how these differences impact their nuclear behavior and regulatory classification. Correct approach analysis. The correct approach involves understanding that the atomic number defines the element and its chemical properties, while the atomic mass, sum of protons and neutrons, is crucial for identifying specific isotopes. For regulatory purposes, particularly in nuclear material control and accounting, precise isotopic identification is paramount. This ensures that the correct safety measures, security protocols, and accounting procedures are applied, aligning with IAEA standards and national regulations that often differentiate based on isotopic composition and associated radiological hazards. This approach reflects best professional practice by prioritizing accurate characterization for effective risk management. Incorrect approach is analysis. Focusing solely on the atomic number without considering the atomic mass would be a significant regulatory and ethical failure. While the atomic number correctly identifies the element, it does not differentiate between isotopes. Different isotopes of the same element can have vastly different radioactive properties, decay modes, half-lives, and radiological hazards. For example, uranium-235 and uranium-238 are both uranium, same atomic number, but have different atomic masses and vastly different applications and regulatory controls due to their fissile properties. Failing to account for the atomic mass would lead to an incomplete and potentially dangerous understanding of the material, violating principles of nuclear safety and security. Confusing atomic mass with atomic number is another critical failure. Atomic mass is a measure of the total number of protons and neutrons, whereas atomic number is solely the number of protons. While related, they are distinct nuclear properties. Misinterpreting these fundamental definitions would lead to incorrect material identification and classification, undermining all subsequent safety and regulatory actions. This demonstrates a fundamental lack of understanding of nuclear physics principles essential for professional practice in this field. Assuming all isotopes of an element have identical radiological properties is a dangerous oversimplification and a direct violation of regulatory requirements. IAEA standards and national regulations are built upon the understanding that isotopic variations significantly alter radiological characteristics. For instance, the criticality of fissile materials is highly dependent on the specific isotope. Ignoring these differences would lead to inadequate shielding, improper handling procedures, and incorrect safeguards implementation, posing severe risks to personnel and the environment. Professional reasoning. Professionals in this field must adopt a systematic approach to material identification. This begins with understanding the fundamental definitions of atomic number and atomic mass and their implications for nuclear properties. When evaluating radioactive materials, the primary step is to determine both the element via atomic number and the specific isotope via atomic mass, often requiring isotopic analysis techniques. This precise identification is then used to consult relevant IAEA safety standards, safeguards documents, and national regulations to determine the appropriate classification, handling procedures, security measures, and accounting requirements. A commitment to accuracy, continuous learning, and adherence to established protocols is essential for maintaining nuclear safety and security. Question 17. Risk assessment procedures indicate that a facility has received a shipment of material containing a specific radionuclide. While the initial radionuclide's half-life is relatively short, preliminary analysis suggests it is part of a longer radioactive series. Considering the IEA emphasis on comprehensive radiological safety, what is the most professionally responsible course of action regarding the assessment of potential hazards associated with this material? Option A. Focus only on the gamma radiation emitted by the initial radionuclide, as this is typically the most penetrating and therefore the most significant immediate concern. Option B. Prioritize immediate disposal of the material to minimize exposure, without a detailed analysis of its decay products. Option C. Assume the hazard is primarily dictated by the initial radionuclide and proceed with standard handling procedures based on its immediate properties. Option D. Investigate the entire radioactive decay series of the initial radionuclide to understand the properties and potential hazards of all daughter products over time. The correct answer is D. Investigate the entire radioactive decay series of the initial radionuclide to understand the properties and potential hazards of all daughter products over time. Explanation. This scenario presents a professional challenge due to the inherent risks associated with radioactive materials and the ethical obligation to prioritize safety and transparency. The core dilemma lies in balancing the immediate need for information with the potential for misinterpretation or alarm caused by incomplete or context-less data regarding radioactive decay chains. Professionals must navigate the complex interplay of scientific accuracy, public perception, and regulatory compliance. The correct approach represents best professional practice because it adheres to the IEA fundamental principles of nuclear safety and security, which emphasize a robust, evidence-based approach to risk assessment and communication. Specifically, it aligns with the spirit of IEA safety standards, which advocate for comprehensive understanding of radiological hazards, including the behavior of radionuclides over time. By focusing on the entire radioactive series and its implications for long-term hazard, the professional demonstrates a commitment to thoroughness and responsible management of radioactive materials, ensuring that all potential risks, including those arising from daughter products, are considered. This proactive and holistic assessment is crucial for informed decision-making and effective risk mitigation. An incorrect approach that focuses solely on the initial radionuclide without considering its decay products fails to acknowledge the dynamic nature of radioactive hazards. This oversight is a significant regulatory and ethical failure because it leads to an incomplete risk assessment. The IEA framework mandates a comprehensive understanding of radiological risks, which includes the potential for daughter nuclides to possess different radiological properties, e.g., half-life, type of radiation emitted, energy of radiation, and thus present distinct or even greater hazards. This incomplete assessment could lead to inadequate safety measures, improper waste management, and a failure to communicate the full scope of potential risks to relevant parties, violating the principle of due diligence. Another incorrect approach that prioritizes immediate disposal without a thorough understanding of the decay products is also professionally unacceptable. This haste bypasses the critical step of characterizing the evolving radiological profile of the material. Ethically, it demonstrates a lack of responsibility towards future generations and the environment, as the long-term implications of the decay series are not adequately addressed. From a regulatory standpoint, it likely contravenes IEA guidelines that require proper characterization and management of radioactive waste based on its radiological properties, which can change over time due to decay. A professional decision-making process for similar situations should involve a systematic, multi-stage approach. First, identify the specific radionuclides present and their initial characteristics. Second, consult authoritative databases and IEA guidance to understand the complete decay chains for each identified radionuclide. Third, assess the radiological properties, e.g., half-life, radiation type and energy, daughter product hazards of all nuclides in the decay series. Fourth, conduct a comprehensive risk assessment that considers the cumulative and evolving hazards over relevant timeframes. Finally, communicate findings and recommendations clearly and transparently, ensuring all stakeholders understand the full scope of the radiological situation. Question 18. System analysis indicates that a research facility utilizing a neutron source is experiencing an increase in background radiation levels that cannot be fully explained by direct source emissions. Considering the potential for neutron capture and activation, which of the following approaches best ensures compliance with International Atomic Energy Agency, IEA, standards for radiation safety and material management? Option A. Implement additional general area radiation monitoring and increase personnel dosimetry without performing a specific analysis of the activation products. Option B. Rely on the general material composition data provided in standard safety data sheets for all materials in the vicinity of the neutron source to estimate potential activation. Option C. Conduct a detailed neutron activation analysis of all materials within the facility that are exposed to the neutron flux, including an assessment of scattered neutrons, to identify and quantify potential activation products and their radiological significance. Option D. Assume that the increased radiation is due to a minor leak in the primary containment of the neutron source and focus efforts on sealing any visible breaches. The correct answer is C. Conduct a detailed neutron activation analysis of all materials within the facility that are exposed to the neutron flux, including an assessment of scattered neutrons, to identify and quantify potential activation products and their radiological significance. Explanation. Scenario analysis. This scenario presents a professional challenge in managing radioactive materials within a facility licensed by the International Atomic Energy Agency, IAEA. The core difficulty lies in accurately assessing and controlling the potential for neutron activation, a process that can transform stable isotopes into radioactive ones, thereby altering the radiological inventory and potentially impacting safety, security, and waste management strategies. Professionals must demonstrate a thorough understanding of neutron physics, material properties, and regulatory requirements to prevent unintended consequences. The challenge is amplified by the need to balance operational efficiency with stringent safety protocols, ensuring that any activation products do not compromise the integrity of the facility or pose a risk to personnel or the environment. Correct approach analysis. The correct approach involves a proactive and comprehensive assessment of potential neutron activation pathways. This includes identifying materials within the facility that are susceptible to activation by neutrons from the primary source, understanding the neutron energy spectrum and flux, and calculating or estimating the resulting activation products and their decay characteristics. This aligns with IAEA safety standards, particularly those related to radiation protection and the management of radioactive waste, which mandate a thorough understanding of the radiological properties of all materials present. By conducting such an assessment, professionals ensure that they can accurately characterize the radiological environment, implement appropriate shielding, monitoring, and control measures, and plan for the eventual disposal of activated materials in compliance with regulatory requirements. This approach embodies best professional practice by prioritizing safety, regulatory compliance, and informed decision-making based on a sound scientific understanding. Incorrect approach is analysis. One incorrect approach is to assume that only materials directly within the primary neutron flux are subject to activation. This fails to account for scattered neutrons, which can reach materials outside the immediate beam path and still induce activation. This oversight represents a significant regulatory failure, as it underestimates the potential radiological hazard and could lead to inadequate shielding or monitoring, violating IAEA principles of radiation protection and potentially leading to the uncontrolled release of radioactive material or exposure of personnel. Another incorrect approach is to rely solely on generic material safety data sheets, MSDS, without considering the specific neutron environment. While MSDS provide general information, they do not typically detail a material's activation cross-sections or the specific isotopes that would be produced under a given neutron flux. This approach is professionally deficient because it lacks the specificity required for accurate radiological assessment and could lead to mischaracterization of activated materials, impacting waste classification and disposal routes, thereby contravening IAEA guidelines on radioactive waste management. A third incorrect approach is to defer the assessment of neutron activation until after an incident or operational change has occurred. This reactive stance is contrary to the principles of proactive safety management mandated by the IAEA. It represents a failure to implement a robust safety culture and a violation of the ALARA, as low as reasonably achievable principle, as it allows for potential risks to persist without mitigation. Such a delay can lead to unforeseen radiological consequences, increased costs for remediation, and potential noncompliance with regulatory obligations. Professional reasoning. Professionals dealing with neutron-generating processes must adopt a systematic and anticipatory approach. The decision-making process should begin with a thorough understanding of the neutron source characteristics, energy spectrum, flux, geometry. This knowledge should then be applied to identify all materials within the operational environment that could be exposed to neutrons, including those indirectly affected by scattering. For each susceptible material, a detailed analysis of potential activation products, their quantities, and their radiological significance should be performed. This analysis should inform the design of shielding, the selection of monitoring equipment, the development of operational procedures, and the planning for waste management. Regulatory compliance is not merely a checklist, but an outcome of this rigorous scientific and safety-oriented process. When faced with uncertainty, seeking expert consultation or performing detailed simulations is a hallmark of professional responsibility. Question 19. Regulatory review indicates that a minor anomaly has been detected in a secondary containment system during routine operational checks. The anomaly does not appear to immediately compromise the primary containment of radioactive materials, but it does represent a departure from the established operational parameters. The facility is currently under pressure to meet a critical production deadline. What is the most appropriate course of action according to the International Atomic Energy Agency's regulatory framework for nuclear safety and security? Option A. Continue operations as normal, as the anomaly is minor and does not affect the primary containment barrier. Option B. Proceed with operations while documenting the anomaly for later review, assuming it poses no immediate threat to primary containment. Option C. Attempt to rectify the anomaly using on-the-spot adjustments by the shift supervisor without formal reporting to avoid operational delays. Option D. Immediately halt operations of the affected system and initiate the formal deviation reporting and corrective action process as per established procedures. The correct answer is D. Immediately halt operations of the affected system and initiate the formal deviation reporting and corrective action process as per established procedures. Explanation. Scenario analysis. This scenario presents a professional challenge due to the inherent tension between operational efficiency and the stringent, non-negotiable requirements of nuclear safety and security. The pressure to meet production targets or cost-saving goals can create an environment where deviations from established safety protocols might be considered, especially if perceived as minor or temporary. The professional challenge lies in recognizing that in the nuclear domain, minor deviations can have catastrophic consequences, and that adherence to the regulatory framework is paramount, irrespective of operational pressures. This requires a robust ethical compass and a deep understanding of the potential ramifications of noncompliance. Correct approach analysis. The correct approach, which involves immediately halting operations and initiating a formal deviation reporting and corrective action process, represents best professional practice because it aligns directly with the core principles of nuclear safety and security mandated by the IAEA regulatory framework. This framework emphasizes a proactive, defense-in-depth approach, where any potential threat to safety or security, however small it may seem, must be addressed systematically. The immediate halt ensures that no further risk is introduced, and the formal reporting process guarantees that the deviation is documented, investigated by qualified personnel, and that appropriate corrective and preventative actions are implemented. This upholds the principle of safety culture, where reporting and learning from deviations are encouraged and institutionalized, preventing recurrence and reinforcing the overall safety and security posture of the facility. Incorrect approaches analysis. An approach that involves attempting to rectify the issue without formal reporting, based on the assumption that it is a minor deviation, fails to adhere to the IAEA stringent requirements for documentation and oversight. This bypasses the established safety review mechanisms, potentially leading to the normalization of deviations and a degradation of the safety culture. It is a regulatory failure because it circumvents the mandated reporting and investigation procedures, and an ethical failure because it prioritizes expediency over the absolute imperative of nuclear safety. Another incorrect approach, which is to proceed with operations while planning to address the deviation later, is a severe regulatory and ethical failure. This directly contravenes the principle of precautionary approach inherent in nuclear safety regulations. It exposes the facility and the public to unacceptable risks, as the nature and extent of the deviation's impact on safety or security are unknown. This approach demonstrates a disregard for the established safety protocols and the potential for cascading failures, which is fundamentally incompatible with professional responsibility in the nuclear sector. Professional reasoning. Professionals in the nuclear sector must adopt a decision-making process that prioritizes safety and security above all else. This involves 1. Immediate identification and assessment of any potential safety or security concern. 2. Strict adherence to established procedures for reporting and managing deviations, regardless of perceived severity. 3. Engaging with relevant safety and security experts for thorough investigation and resolution. 4. Ensuring that operations only resume after all identified risks have been mitigated and regulatory approval is obtained. 5. Fostering a culture where open communication and proactive reporting of issues are encouraged and rewarded rather than penalized. This framework ensures that decisions are grounded in regulatory compliance, ethical responsibility, and a commitment to preventing harm. Question 20. The evaluation methodology shows that when analyzing the operational characteristics and safety implications of a typical pressurized water reactor, PWR, which of the following comparative analyses of nuclear reactions is most critical for a comprehensive understanding? Option A. Distinguishing between nuclear fission and nuclear fusion processes and their respective energy generation mechanisms. Option B. Focusing exclusively on the chain reaction aspect of fission without considering neutron moderation or absorption. Option C. Identifying all possible radioactive decay products of uranium and plutonium isotopes without considering the initiating nuclear reactions. Option D. Differentiating between neutron-induced fission reactions and spontaneous radioactive decay and understanding the role of neutron capture in the fuel cycle. The correct answer is D. Differentiating between neutron-induced fission reactions and spontaneous radioactive decay and understanding the role of neutron capture in the fuel cycle. Explanation. The evaluation methodology shows that understanding the fundamental principles of nuclear reactions is paramount for ensuring the safe and secure operation of nuclear facilities, as mandated by the International Atomic Energy Agency, IAEA safety standards, and relevant national regulations that implement these standards. Professionals are challenged to differentiate between various nuclear reaction types and their implications for reactor physics, radiation shielding, and waste management. This requires a deep conceptual grasp beyond mere memorization, enabling them to apply this knowledge to real-world scenarios involving reactor design, operation, and accident analysis. The correct approach represents best professional practice because it demonstrates a comprehensive understanding of nuclear reaction physics, enabling accurate assessment of reactor behavior and associated safety implications. This aligns with IAEA Safety Standards Series No. SSG 20, Application of the Management System for Facilities and Activities in the Nuclear Sector, which emphasizes the need for competent personnel with a thorough understanding of the technical aspects of nuclear operations. Specifically, it supports the principle of defense in depth by ensuring that potential hazards arising from different types of nuclear reactions are correctly identified and mitigated. An incorrect approach that focuses solely on fission reactions without considering other relevant nuclear processes, such as neutron capture or decay, fails to provide a complete picture of reactor physics. This oversight can lead to miscalculations in neutron flux, criticality assessments, and the buildup of radioactive isotopes, potentially compromising safety margins. Ethically, this represents a failure to exercise due diligence and a lack of professional responsibility in ensuring comprehensive safety analysis. Another incorrect approach that conflates nuclear fission with nuclear fusion in the context of current power reactor operations is also professionally unacceptable. While both are nuclear reactions, their mechanisms, energy release, and technological implementation are vastly different. Misunderstanding this distinction can lead to flawed assumptions in reactor design, fuel cycle analysis, and safety system design, potentially resulting in inadequate protection against specific hazards. This demonstrates a fundamental lack of understanding of the core principles governing nuclear power generation. A further incorrect approach that prioritizes the identification of reaction products without understanding the underlying reaction mechanisms and their associated energy releases is also flawed. While identifying products is important for waste management and material analysis, it is the understanding of the reaction itself, the initiating particles, the energy involved, and the probability of occurrence that is critical for predicting reactor behavior and ensuring safety during operation. This approach neglects the predictive and preventative aspects of nuclear safety. Professionals should employ a decision-making framework that begins with clearly defining the scope of the analysis and the specific nuclear processes relevant to the scenario. This involves consulting IAEA safety guides and relevant national regulations to identify all applicable nuclear reactions and their potential impacts. A thorough understanding of the fundamental physics of each relevant reaction type, including their cross-sections, energy dependencies, and product yields, is essential. This knowledge should then be applied to assess reactor behavior, radiation fields, and potential accident scenarios, ensuring that all safety aspects are comprehensively addressed.